The topic is Introduction to Wind Energy Conversion System. In this topic, there are three major areas which we have to focus. First area is power wind speed characteristic. Next is fixed speed and variable speed wind turbine. Third one is challenges with grid interconnection or grid codes. So coming to the first point, before then, this is the first point. Before that, I want to share some components of wind turbine. These are the blades which are mounted on rotor hub. Then there is connected this low speed shaft that is connected to gearbox, and then to generator and power converters are connected as well. So the main part in this component series is gearbox, which converts the low speed shaft to a high speed shaft. Actually, it increases the speed of the wind turbine, and also the torque which is generated and the pulsation of the torque are made to reduce in this particular section. So this was all about the components. Next is power wind speed characteristic. This is the power wind speed characteristic, which is this is cut-in speed and this is cut-out speed. From cut-in speed, the mechanical power of wind turbine is converted to electrical power, and this is the cut-out speed. At this speed, no mechanical power can be converted to electrical power, because the electrical section is made to cut out with that of mechanical section. This is the shaded region. Shaded region is the operating region of generator or the wind turbine. In this particular region, there are two types of control on which the wind turbine could be controlled. First is generator control, and second one is stall or pitch control. The generator control depends upon the relation which is given over here, P air equals to 0.5 rho A V cube. So you can see that the power which is generated in this wind turbine, that is directly proportional to the cube of velocity of wind. So as the wind speed changes, it makes a drastic difference on the power generation, that is P air. Now there is one more. You can see that rho is air density in kilogram per meter cube, V is velocity of wind in meter per second, and A is area swept by the blade in meter square. Now there is one more conversion coefficient, that is Cp. This is power coefficient, and it is defined as P wind turbine divided by air. It is the ratio. It is actually the ratio, and it gives the comparison that how much the wind turbine generates the power and how much the power is given to the turbine by the wind. So it's a constant, and generally it has a value from 0.25 to 4. So this is the overall relation for wind turbine. Now coming to this characteristics again. In this characteristic, the operating region in the pitch or stall control, what we do in this particular control, as the wind strikes over the blade is made to move either in the direction of the wind or out to the direction of the wind. If it is made to direction into the wind, then certainly it comes under the active control, and if it moves out of the wind, that is mostly used in wind turbine techniques, that is called as pitch control, and we use this particular technique beyond the rated value of wind speed. Up to the rated value of wind speed, what we need to do, we just track out the wind velocity, and according to that wind velocity, we just change the speed of turbine so that the maximum energy of turbine could be harnessed and given to the generator. So this was all about power wind speed characteristic. Now coming to the next one, that is turbine configuration. In this turbine configurations, there are two types of turbine what we use. In 1980s, we used fixed speed wind turbine that was considered to be move at fixed speed. The reason was that it was used with the squirrel cage induction generator, and a squirrel cage induction generator made to operate at a particular synchronous speed. Now, it was desirable that wind has to flow or blow according to the need of the RPM which is needed by the generator that was being needed. So in this particular wind turbine, we have some problems. Thereafter, we go on some modifications over the turbine, and we have gone to adjustable speed wind turbine or variable speed wind turbines. So in this particular section, we have two wind turbine. First one is doubly fed induction machine based on reduced capacity, and second one is permanent magnet synchronous machine based VAX, which is full capacity. Now this is reduced capacity and full capacity in terms of power conversion. Let us go it one by one. First is fixed speed wind turbine. In this fixed speed wind turbine, we can see that this is the wind aerodynamics connected to the gearbox, and gearbox is connected to squirrel cage induction generator. Now the power generated, the electrical power generated by the squirrel cage induction generator, that is being transferred to the grid by using soft starters and power factor compensation and transformer. These are the components which drives the power or controls and put the power in that particular format which is needed by the grid. Now there are some conditions of fixed speed wind turbine. The power conversion is possible at the rate of 1%, that is, it is the band limit near the synchronous speed. If the turbine speed or the rotor speed goes beyond 1%, plus minus 1% of the synchronous speed, then certainly the squirrel cage induction generator would not able to produce the required frequency of power. So it is rigorously needed that the squirrel cage induction generator must be provided fixed speed of shaft. So, but the few points are also there. The construction and performance of fixed speed wind turbines vary much, depends upon the characteristic of mechanical subcircuits, that is pitch control, minimum circuit breaker, etc. Mean to be that most of the controlling in a fixed speed wind turbine is regarding the mechanical construction. It doesn't go with the stall or something pitch control mechanism. Also in fixed speed wind turbine, as a squirrel cage induction generator is used, we need to give the reactive power to the machine. So we have to provide capacitor bank or STATCOM or DVR or something which could produce the reactive power and fed to the squirrel cage induction generator. Reason is that for the generation of power, the electrical flux that is need to be set up in the generator, that need some power, reactive power at a low power factor, and that power factor that is at low power factor, that reactive power is need to supplied by some source, battery operated source or grid operated source. So this was the constraint with the fixed speed wind turbine. As the problem was that it severely undergoes the tripping mechanism because of the variation of the wind speed. So what we do, we go for some modifications and just use some variable speed wind turbine techniques. First one is doubly fed induction generator. In this particular induction generator, wound rotor induction machine is used, and this induction machine is at rotor. You can see that it is connected to back-to-back converter. This is rotor side control, this is a grid side control, and the stator of that DFIG or DFIM is connected to the grid. Grid is all not shown here, but you can visualize it very well. Pitch control drives the gearbox and the rotor blades so that the regulated speed could be obtained at rotor. Now in this particular configuration, we can go for the 30% plus and minus, both in subsynchronous as well as supersynchronous. Let me define that. Subsynchronous mode, the rotor speed is below the rated speed, that is called as the synchronous speed. In super synchronous mode, the speed is operated above the synchronous speed, that is called as a super synchronous mode. Now in both of these cases, the doubly fed induction generator generates the active power and it delivers the active power to the grid. Whereas the difference in these two is that in subsynchronous mode, the rotor power, the power conversion from grid side or rotor side is that is rotor power. It is obviously around 25 to 30% of the main power, which is transferred from stator to grid. Now this is the rotor power which circulates in the subsynchronous mode. It moves from the grid, then GSC to RSC, then to generator, and then to converts to the stator, and then to the grid. Now whereas in super synchronous mode, stator as well as rotor both produces the stator power and rotor power, and then at a particular point of common coupling, they both power comes to be at one place and fed to the grid. Now these two converters are operated as per the need of the wind speed or the voltage, if that varies according to the load or any faulty conditions or some problems when occurs. So these are the two converters on which the rotor power is made to control and plays a very important role for the power conversion from DFIM. The next one is permanent magnet synchronous machine based wax. In this particular configuration, you can see that this is the gearbox and it is connected to permanent magnet synchronous generator as well. Now these are the back-to-back converters which are connected at a stator, and full power, electrical power, is controlled by these two back-to-back converters and then fed to transformer and then to grid. The advantage of this particular full capacity converter is that it can convert power of every wind speed to electrical speed, because the reason is that when the wind speed varies at the aerodynamic turbine, according to that, the frequency or the voltage which is generated at the permanent magnet synchronous motor, that can be converted to a DC power. As we can see that this is the DC link and this is the incoming this is at wind turbine connection and this is at the grid connection. So every power or the variable power or from the variable wind speed, that is converted to DC power, and then DC power is regulated, and this regulated DC power is converted to AC power of a fixed frequency on a fixed voltage and then fed to grid. So this DC link gives a complete isolation from wind turbine mechanical power and the generated electrical power, the pulsation and all that, to that of well defined or better quality power based electrical power to grid. So as we can see that permanent magnet synchronous generator employed with this wind turbine is fully controllable by use of power converters, and for any wind speed the power generator is converted to a standard frequency by using back-to-back converter. Now one more point is there to compare in DFIG and variable speed wind turbine, as the full capacity converter is better than that of doubly fed induction generator, but the reason is that the power converter rating which is used in full capacity would be of a standard voltage and power, such that if we are using 1 megawatt of power from wind turbine, then 1 megawatt of power should be there for power converters which are used in full capacity. But if we are using 1 megawatt wind turbine to DFIM, then only we need to go for 0.25 megawatt rating of power converters in rotor side converter, and then we can go for the power conversion as well. So there is economic, we can say that W5 induction generator power converters are much more economic than that of full capacity based converters. Now come on to the challenges with the grid interconnection. In this, the challenges with the grid interconnection to such kind of wind turbines are that as the wind is intermittent in nature, it changes, so as the voltage and the frequency of the generator output changes. So if there is a drastic difference between the wind speed, then certainly the voltage fluctuation will occur, and this voltage fluctuation is called as flicker, which is a power quality problem and not acceptable as per to the IEEE standards. Now one more problem is there. When the wind speed goes down and just collapse to a very low value, less than that of cut-in value, the low voltage right through, this is the grid code which is given by the utility to the distributed generation systems to follow that. In this particular section, when wind turbine is made to trip, there are, such as in the faulty conditions, some fault occurs. Now the wind turbine is not just made to trip as that particular instant when the fault occurs. Under this condition, the grid just sense fault, what kind of fault is that, if it could be recovered or not. So this is the shaded region. You can see that in the shaded region you can disconnect, you must connect the wind turbine to the grid, and if the time elapses more than that of 150 microseconds or 150 milliseconds or 700 milliseconds, then certainly the fault comes to be a severe, and that particular fault or fault current can need to be abrupt the system, so it needs to clear. So when this condition occur, certainly we will go for the fault clearance, but up till that LVRT is used for deciding that the wind turbine should go for tripping or not. So this point, reduction of torque pulsation, that are the electromechanical and load torque operating at wind speed. So according to the wind speed, the torque pulsation occurs, and we need to just make the smooth torque so that the power could be converted easily, and power quality could be obtained easily. If such a system is connected to weak power grid, then certainly in a faulty condition, overspeeding of the wind turbine as well as the rotor goes to the unstable region, and certainly in this particular section we just cut out the wind turbine or the wind turbine power, and the contingency occurs. So this particular point is related to LVRT. The LVRT is needed to define such a to tripping of contingency. The last part is voltage frequency or power frequency constraint. You can see that this is the line voltage, this is the frequency. If the variation of the frequency with the line voltage is going out in this particular section, that we can say that if the frequency is increasing and also the line voltage is disturbing from its values, say that 380, 220 or 110, then certainly some time is allotted so that it could restore its particular condition, and if it does not go for this times which is given over here, that t equal to 30 minutes or 30 minutes over here, and also this is the 20 minute and this is for 10 minutes. So for these time constraints, If the system do not restores itself, then we will surely go for the tripping and disconnect the wind turbine from the utility. Similarly, in this power versus frequency relation also, frequency of the electrical power that needs to be maintained at 50 Hz, and if it goes beyond 50 Hz or less than that of 50 Hz, then certainly the power quality needs to be checked and turbine characteristics need to be changed. So these are the normal operating conditions, these are the required. And if for a very short term, if the faulty conditions, if the system gets restored, then very well, then otherwise we will go for the tripping of the system. So these are the some few challenges and problems which are occurred in wind turbine technology. For the further instance, you can refer to these conditions, these references, and thank you for watching this.